Alright, so this video is going to focus on Hess's law and enthalpies of formation. So we're going to be looking at enthalpy calculations. Hess's law states that if a reaction is the sum of two or more reactions, the enthalpy for that process is equal to the sum of the enthalpies of your other reactions. So basically you are taking reactions and combining them to form a new reaction, and that's the one that you're trying to find the enthalpy of. And if you know the enthalpies of the original reactions, depending on how you have to manipulate them, you can calculate the enthalpy of the reaction that you're trying to find out about. If you reverse a reaction to make that work, you are switching that reaction from being endothermic or exothermic or vice versa. So the enthalpy sign would need to be reversed as well. And because, as we've seen already in this unit, enthalpy is directly dependent on the amount of materials you have and the heat that is released by those materials. If you adjust a coefficient by a factor, and I said here if it's multiplied by an integer, it could be multiplied by a fraction as well, you would need to account for that with your enthalpy values. So if you have to adjust all of your coefficients by a factor of 2, your enthalpy values would be multiplied by that factor of 2. If you had to adjust all of your coefficients by a factor of 1/3, then your enthalpy would have be multiplied by that value as well. So here we have 3 reactions. We see, trying to do the math in my head, I want to say that that is ethine. Combusting, you have carbon combusting and you have hydrogen combusting. And you are given the enthalpy values of those 3 reactions. And we want to calculate what the enthalpy of the reaction would be when carbon and hydrogen produce ethine. So when you are in a scenario like this, the first thing I always look for is the most straightforward approach. Try to find what I want to have present in my overall reaction. And as long as there's only one of those particular reactants and products present, it's a pretty straightforward process. So if I look at my 3 reactions, I see that there is only one that has carbon as a solid. That would be my second reaction. And that it has 1 carbon present in that reaction. And I need 2. So I'm going to double all of the reactant and product quantities in my reaction, and I want to multiply my enthalpy value by a factor of 2. Because carbon was on the reactant side of my equation, which is what I wanted to have present, I don't have to change the sign of my enthalpy. Next, I'm going to look for my next reactant to see perhaps if I can get away with just setting that equation up. And I do say that in my third reaction, and it has the right stoichiometric amounts, and it's on the correct side of the equation for the one that I want to make. Oh, I just doubled it there. Sorry, y'all. Had to double check myself for a second. Because I had initially 2 times everything, I went ahead and doubled it so that you could see what the change would be and what the new enthalpy would be once it was doubled. Hydrogen, that's not going to have to take place because hydrogen is on the correct side. It was already in the correct stoichiometric amounts. So I can just leave that reaction as is. My final component of my reaction is my product, C2H2, and that is in that first reaction. So that worked out really well, but it's on the incorrect side. It's on the reactant side, and I want it to be on the product side. So I'm going to take this reaction and reverse it so that CO2 and H2O are going to be on the reactant side. C2H2 and the 5/2 oxygen are going to be on the product side, and my enthalpy value will change from being exothermic, negative 1300 kilojoules, to endothermic, positive 1300 kilojoules. If this has been done correctly, all of the other reactants and products in these 3 equations that are not in the reaction I am trying to find out the enthalpy for should cancel themselves out. They should either be formed initially as products and then consumed as reactants, or vice versa. And if I take a look at this, I see that the oxygens do indeed cancel out. 2 1/2 would be 5/2 oxygen. I also see that that's going to happen with my liquid water molecules as well as my CO2 gaseous molecules. And so now I'm left with 2 carbons and 1 hydrogen forming C2H2. And I would add all 3 enthalpy values together to get the enthalpy of that particular reaction. 226 kilojoules of heat would be needed to generate 1 mole of ethine. The bombardier beetle is going to use this explosive discharge as a defense measure. And the chemical reaction that is able to generate that, hydroquinone, is going to be involved in the oxidation of hydroquinone by hydrogen peroxide, produces quinone and water. And so this is the reaction we want to try to find the enthalpy for, and we're given 4 reactions that we can use to find that enthalpy value. So again, I start looking for my reactants. If I find a reaction with the reactant by itself, in this case I did with the first equation, I go ahead and use that one. This is set up in the correct stoichiometric amounts and on the correct side of the equation. So there is our first reactant. And then we have H2O2 also as a reactant. And if you look at your remaining equations, I see in the second equation a hydrogen peroxide molecule. It's the only other one I see one in, but it is on the wrong side of the equation. It's on the product side. We want it on the reactant side. So we're going to switch H2O2 and have it produce hydrogen and oxygen, and our enthalpy value will be changed in sign from negative to positive. Our first product is already set up for us. It was part of the first equation. And now we have liquid water. And there's only one equation with liquid water, so that worked out pretty well as well. When you run into a situation when you have a reactant or product that's found in multiple equations, sometimes I have to use some of those intermediates, the ones that aren't present in the final equation, to be able to get everything set up. And I think you may run into that in some of your practice problems. In this particular problem, we do have H2O as a liquid on the product side, which is how we want it to be. It's only in one of my equations that I have remaining. It was not present in any of the equations I've used so far. It is not in the correct stoichiometric amount. I need twice the amount of water, so I would double the coefficients for my reactants and products in that equation, and that would cause my enthalpy value to be doubled as well. If I take a look at the 3 equations I have hydrogen molecules, oxygen molecules, and gaseous water molecules present, and none of those I want to have in my overall final equation. There was one equation I had yet to use, and that was the third equation. If I take a look at the 3 equations I have written so far, I see I have 2 hydrogen molecules as products, 1 oxygen molecule as a product, and 2 gaseous water molecules as reactants. Well, I want to cancel those out. So I do believe if I take a look at that third equation, it is set up correctly for that canceling process, but it does not have the correct stoichiometric amounts that I want to cancel. I need to double the amount of hydrogen and oxygen and water that's present in that third equation, which would mean that I need to double my enthalpy value so that I can stoichiometrically remove all hydrogen, oxygen, and gaseous water molecules from this set of equations. And by doubling it, I was able to do that. The 2 hydrogen molecules canceled, the 1 oxygen molecule canceled, and the 2 gaseous water molecules canceled. I go ahead and take my reactants and my products, put them together, add up my enthalpy values, and I get the overall enthalpy value for this particular equation. So this last part here is going to involve enthalpies of formation, how we get these enthalpy values for a reaction. And we are able to determine the enthalpy values for a reaction from the enthalpies that were needed to form our substances by determining how much an enthalpy was needed for a substance to be formed, either through bonds or through changing state if it was outside of its standard state of matter. Once we have these enthalpies of formation, we can take the amount of substances present stoichiometrically in our equation along with their enthalpy values of formation and take that sum of those for the products and subtract it from that of the reactants to get the enthalpy values for our reaction. If you happen to have elements in your standard state, so such as aluminum as a solid, bromine as a liquid, helium as a gas, those would not have enthalpy values of formation other than 0 because they do not have any energy requirement needed or any energy that needs to be released for them to exist at 25 degrees Celsius and 1 atmosphere of pressure. And these are going to come from that chart that I've shared with you previously in class. I'll pull that up real quick. I'm sorry I didn't think about it. I should have had this up sooner. We're going to make my life a little easier. And hopefully yours too. So if we go over to your Google site, it would be on those thermodynamic tables there. Again, if you were in class, you got a set of these. If you're not, you have them available to you virtually. We're going to be focusing just on that first column, but here you can see there's bromine as a liquid with a 0 assigned for its enthalpy of formation, cadmium as a solid, calcium as a solid. Elements in their standard state at room temperature have enthalpy values of 0 because there is no enthalpy associated with them forming, since that is how they are naturally found. So you're going to use that chart I just showed you, find these different substances present on that chart, and calculate the enthalpy for this reaction. So if I go look at that chart for these 4 substances, I would find ethanol's enthalpy, carbon dioxide's enthalpy, and gaseous water. You do want to make sure you pay attention to your state. And remember with oxygen, because it is a gas at standard temperature, it would have an enthalpy of formation of 0. On any sort of assessment, I would not have to give you enthalpy values for elements in their standard state because, yes, you should know what those enthalpy values are. If it was any other substance and you needed it to find the answer, you would be provided with that information. So again, we're going to take our products and we're going to multiply their enthalpies of formation by the amount of those substances present, their coefficients, and then we're going to subtract that away, subtract the reactant enthalpies and coefficients, the sum of those values, away from the products. So I have 2 moles of CO2, 3 moles of water, and I'm going to take away from that 1 mole of ethanol and 3 moles of oxygen. Make sure that negative that you are using to take the products or reactants away from the products gets distributed to both reactants, especially if they both have enthalpy values. At this point, the moles all cancel, and I do my math. I multiply and divide, and I get that my enthalpy for this particular reaction is negative 1234.8 kilojoules. For sig fig purposes, those coefficients do not have a measured quantity. They are a defined quantity based on the coefficients in the balanced equation. So when we multiply, we just want to keep our sig figs, and then we add and subtract. We go with the measurement with the fewest decimal places. They all had 1 decimal place, hence why our enthalpy is out to 1 decimal place. This is just another example of that type of calculation. Nitroglycerin is not in your chart, so I did provide you with its enthalpy of formation. We already know about nitrogen and oxygen because they are elements in their standard state. Carbon dioxide was the negative 393.5. The gaseous water was the negative 241.8. And then we're going to subtract away from all of those products our 1 reactant, negative 364 kilojoules per mole, was its enthalpy of formation times the amount of moles present too. All the moles cancel. I do my multiplication and addition along with my subtraction, and I get negative 2842 kilojoules. This one did not have a decimal place because of that negative 364. The only other way I could ask you a question involving enthalpies of formation would be to ask you to find one of the reactants or products' enthalpies of formation if you were given the enthalpy of the reaction. And you know that this is this enthalpy of the reaction because it specifically says combustion. Combustion would be a reaction where we're taking, in this case, ethane and reacting it with oxygen. And when we do that, is going to produce carbon dioxide and gaseous water. We want to find, it says, what the enthalpy of formation is for C2H4. So we know what the enthalpy is for this particular reaction, and we can use our chart to find the enthalpies of CO2 and H2O. So those are included there. 2 times the negative 393.5 for CO2, 2 times negative 241.8 for H2O. We don't know what the enthalpy of formation is for C2H4. We know oxygen has an enthalpy of formation of 0. And that when we do our multiplication and then our summing, subtracting products minus reactants, all of those enthalpy values should equal that negative 1411.1 kilojoules. So if I go through and do my math, this would be one that you may want to do on your calculators, or you can do old school addition, subtraction, multiplication, and you will get that your enthalpy for this particular reactant, its formation enthalpy, is 140.5 kilojoules per mole.